did you see? Something evil?
Excitement, confusion.
As an introduction to this idea, we're going to look at an equation whereby we have half of the derivative of some function y equals f of x gives us the answer x, and more importantly we're asked to find the general solution. Now we'll explore this a bit more later, but general alludes to the fact that there is variability. There is no fixed particular solution, it's a broad range. And you'll see what this means as we go through the process. What we have here is a differential equation, and in plain English this is telling us that 1/2 of the derivative of some function y, which is given in terms of x, as we have dx here, must be equal to x. And we've seen expressions, or beg your pardon, equations like this before, but we've not discussed them in the context of differential equations. This is something new. And what our aim is to try and establish what this function y actually is. The function y whereby if you take half of its derivative, you get x. So we're finding functions, not values. And we're going to see how the functions and their derivatives relate. I mean, we could express lots and lots of different types of equations like this in terms of the derivative of a function, and they can become very, very complicated, and it's kind of like the pinnacle of what you would be doing at this level of maths. But we'll start off with this example, and this is a nice place to start because it will hopefully tease out some of the key concepts. So let's just jot down what our aim is. Remember, we want to find out what this function y actually is, and it's got to be expressed as a function of x. So I'm going to write that down. So we're going to find y, and that's equal to f of x. This is in your notes, of course, I'm just reiterating it. That's our target. Well, we know a lot about algebra, and we know we can do a bit of manipulation here. So a good strategy might be to make dy by dx the subject, because we don't have dy by dx on its own, and that would make hopefully finding the original function a little bit easier. So let's have a look what we can do. Well, we've got half there. Let's multiply both sides by 2. Let's do that. So if I do that, I'm going to have dy by dx on the left hand side of this equation. And if I double the right hand side, I get 2x. Now that looks a lot more familiar. Now that might have been the answer to a question that you've done previously. The question is now, how do we get the original function? Well, we know a little bit about integration, don't we? Clearly, if I have the gradient function, I'm going to have to do some integration. So I could just say, well, okay, if I integrate both sides, therefore I've got my y. Let's do that. So the integral with respect to x, of course, of dy by dx is just y. And if I integrate 2x, well, that's a standard year 1 integration question. So I add 1 to the power. Let's do that. So the power of x is, of course, 1. So if I add 1 to that, I'll get 2x to the power 2, and then I divide by the new power, and then I have to remember to add the constant of integration, like so. Right, now let's just make that look a little bit more simple. So we have y equals x squared plus the constant of integration. That's fine, that's given us the answer, but I'm not particularly happy with this jump from dy by dx to y, I'm sure there's more going on here. This is just from experience, of course, but is there an algebraic step that will get me from dy by dx to y? Well, let's just explore this. I'm just going to do an aside over here. So if I take this step and think about what's happening, well, I know I've done integration because I've done integration in my head, because I can see it's an integration question. But why is this the case? I mean, why does dy by dx integrate to y, and then we just apply the rules on the right hand side? So it's more the left hand side I'm interested in. Well, the reason is because we can treat these dy and dx as objects. They're actually called differential forms, which we're not going to go into in this course. But if I treat them as objects, that means I can manipulate them in the same way as a constant or an x or a y, whatever it is. So what I could do is take that dy by dx and multiply both sides of the equation here by dx. Okay, so I'm going to do that. So I'm going to have dy is equal to 2x dx. There we go. So this is a small change in y, this is a small change in x. That's what it represents. What will happen then if I integrate both sides? Well, let's do that. So if I integrate both sides, just get my green pen here. So if I integrate, I'm going to integrate dy like that. So I'm allowed to integrate the left hand side as long as I integrate the right hand side, then the nature of the equation doesn't change. So that's going to equal the integral of 2x dx. Like that. Now then, we could look at either side and treat them just as a standard integration question. If I integrate dy, the small change in y, I'm essentially, if you remember, integrating 1 because I've got one lot of dy. But I'm integrating the variable y. I'm not integrating x, I'm integrating with respect to y. So that means if I integrate 1 with respect to y, I'm just going to get y back. So this becomes y once it's integrated. And on the right hand side, I'm integrating 2x with respect to x. Okay? And that's the standard result. So that's where the x squared plus c comes from. Now, you might be asking, well, that's great, but why don't you add a constant on the left hand side as well? Well, the reason is really simple. Let's just suppose I did that. Well, so if I said, okay, it should really be y plus a constant, I'll call it c1, and that's equal to x squared plus another constant c2. What I've effectively done is I've added a constant to both sides. Now, there's no point doing that. What if I combine the two, I would have y equals x squared plus c2 minus c1, which is just a constant. So I could just call it c and just add it to one side and just not have to deal with this unnecessary step. So that's how you would integrate a gradient function like this. And we're going to look a bit more in depth at this in later examples. What I'd like to show you now is a graphical representation of what we mean by general solutions or a family of solutions. And the green curve you can see in front of you is the curve y equals x squared with y-intercept at the origin. And you can see here that we've set the c value, the y-intercept, at 0 specifically, and we have a slider here which we can vary our c. What will happen is if I put the trace function on and just drag this c to make it more positive, up to 10, you can see this generates a whole host of possible solutions, because as you vary the c, this will translate the curve y equals x squared vertically by the vector 0, c, whatever the value of c is. And if I drag it back down, I can create more solutions. So you may intuitively see that there is an infinite possibility of solutions here. As long as I can vary my c and choose whatever I want, the general form will follow this pattern, but there is no way I can pick out a particular solution unless I select a particular value of c. So such as, let's say 1.8, for example, that will fix me at a particular position. So this would be what you would call a particular solution. But when you enable the variability of c like this, you have a whole host of possible solutions, and this would be the family of solutions, the infinite set of all the curves y equals x squared plus c. So I just wanted you to see that, just to give you an intuitive idea of what we're talking about. Now that we have established a general solution for this differential equation, we need to find a particular solution, and as I've already stipulated, this requires additional information. So given that x equals 1 when y equals 3, we should be able to establish what the constant c is and therefore what our particular solution is. Now that we've talked a bit more about what a general solution actually means and how it generates a family of solutions, we can now move on and try and determine some kind of particular solution. So that means we strip away the infinite possibility that there are an infinite number of curves, y equals x squared plus c, where the constant varies, and we pin it down to one specific solution. And to do that, we're going to need a bit more information, aren't we? Because obviously when you differentiate, and especially when you start off with a derivative, there's information missing about the original equation because the constant is lost in the differentiation process. Now, this is perfectly adequate to solve this equation here, because if I differentiate y, the constant will disappear or become 0, and the gradient is of course 2x, and half of 2x is of course x. It's simple to check that in your head. But what if I want to find a specific solution? Well, more information is needed, and this information is sometimes referred to as a boundary condition, or if you need more information, that boundary conditions, the plural. And the boundary condition we have for this, which is supplied to us, is that we're told that when x equals 1, y equals 3. Well, that's good. So that means I can add this information and hopefully nail down a particular solution. So when x is 1, I'll just write it down, x equals 1, like that, then y equals 3. Okay, great. So how do we find our specific solution? Well, it's pretty obvious, I think. We just substitute in those values and then determine the value of the constant c. So well, I'll just make a note of that because you need to remember how to do this. So sub values into y equals x squared plus c. Okay, we can do that. So we know y equals 3, so we'll start off with that. And 3 must equal x squared, which is 1 squared, which is of course 1, but I'll write 1 squared so it's clear. That's 1 squared plus the constant of integration. So in other words, 3 equals 1 plus c. Subtract 1 from both sides, so c must be 2. And there we have it. So we've got our constant c as 2. That means we can state our particular solution. So the particular solution in this case I'll use my shorthand for solution, like that. It will be y equals x squared plus 2. So with the added information we can complete the question. Example 2, we are again asked to find a general solution to a different differential equation this time. And because the complexity has been increased slightly, I'm going to introduce a three-step process which you can follow, which will hopefully make solving these differential equations a little bit more straightforward. So step 1, which is what I recommend you do if necessary, is to make dy by dx the subject of the equation. The second step is the process that this lesson is about, which is separation of variables. And what this means is you need to put all the y variables on one side of the equation and all the x variables on the other side. Now I've stipulated left and right, left for y, right for x. You don't have to do that, it's up to you, but you have to make sure that the variables are separated by the equal sign. Step 3, we go back to integration. So you would integrate both sides of the equation. So this is a slightly more complicated scenario. I've just made a note here. We're going to find the general solution first. This is part A. And as you can see in the way I've set out, or set up the question, I've given you 3 steps to follow. And it's important that you do this because it will just make the solving differential equation process a whole lot easier. And if we look at step 1, our first task is to make dy by dx the subject. Okay? Sometimes dy by dx will be the subject, so you can skip that, but in this case we are going to have to do a bit of manipulation. Okay, so we can see we've got dy by dx plus x over y is equal to 0. So I'm going to subtract the x over y from both sides of this equation first. Now that will make dy by dx a subject. Let's do that. So we're going to have dy by dx and because I'm subtracting from both sides, that's going to give me negative x over y. Now this may look familiar if you've done the preparation task. What now? Well, this is the key step. We're going to have to separate the variables. Now what that means is I need to get all the y variables on one side and all the x variables on the other. And it's not standard practice, but it's good practice to maybe keep the dy on the left and we'll put the dx on the right. So y is on the left, x is on the right. And I'll make a note of that. So over here, we're going to put the y stuff over here and we're going to put the x stuff over here. Alright, so that means I can leave dy there. I'm going to have to do something with the dx and I'm going to have to do something with the y on the right hand side. Well, let's just deal with the left hand side first. I'm going to keep the dy. In fact, I'm going to move over here so we have a bit more space. So we're going to have dy. That's staying. Now to remove, if you want to use that terminology, if I want to remove the dx, I'm going to have to multiply both sides of the equation by dx. Alright, so this is going to give me negative x over y, and I'll just put the dx in red to show that I've multiplied both sides by it. So that's going to be the next step. Okay, now I've got a dy on that side. Now you can see now I've got a y variable on the right hand side. So we have to ask ourselves, how can I make the y variable migrate somehow from the right hand side to the left hand side of the equation? Well, it's the same idea. We're going to have to multiply both sides of this equation by y. So that will be the next step. And I'll just do an implies arrow just so we don't run out of space. So if I multiply both sides by y, let's do that. So I'm going to have y, and then the dy that I already had is equal to negative x dx. Okay, let's just do a check. So y stuff on the left, yes, good. X stuff on the right, great. We're now in business. Once we've done that, we can now integrate both sides of the equation as we did in the previous example. So our next step is, of course, to integrate. Let's just add some integration signs. So this will be the next step. So we're going to integrate y with respect to y, so y dy, and that's going to equal the integral of negative x. Now what you could do is you could bring the negative outside. I won't do that, I don't want to overdo it in one step. So we're integrating negative x with respect to x. Just put the dx on there. Great. Now then, let's perform the integration. So I'm integrating y with respect to y. No problems there. It's a standard integral. Don't worry that it's a y variable because we're integrating with respect to y. That is absolutely crucial that you're comfortable with that. That's why this is so important. Okay, so I'm integrating with respect to y. So I apply standard integration techniques, add 1 to the power, divide by the new power, year 1 stuff. Let's do this. So we're going to have, so I'm just following on here. So y squared over 2. And no need to add the constant, we can do that on the left hand side. Okay, remember I explained that previously. Y squared over 2, add 1 to the power, divide by the new power. The left hand side is integrated. That's going to equal, now negative x, okay, but it's just 1 power of x, so I add 1 to the power, again divide by the new power. So it's going to be negative x squared divided by 2. All right, and plus a constant. Right, now this is where we just pause for a second. Now we have a general solution, technically speaking, were we asked to find it in a particular form, i.e. were we asked to give it in the form y equals f of x. Now if you look at the question, the answer is of course no. So we're pretty much done, but there is something I do want to point out here. If you've done the preparation task for this lesson, preparation task 8, you will have done a differentiation which should have taken you to this result here. And if I just do a little bit of manipulation, I'm going to leave that as it is, but if you think, how can I make this look a bit neater? Well, I could multiply both sides by 2, that would clear the 2 on both sides. So this is, I'll put this in brackets, because this is not necessary, but it's something I want you to be aware of. If I multiply both sides by 2, I'm going to have y squared is equal to negative x squared plus 2c. All right. Now, what I'm going to do is I'm going to add x squared to both sides. So therefore, x squared plus y squared is going to equal 2c. Why is that interesting? Well, this is a circle. We have x squared plus y squared equals 2c. So in other words, it's a circle, but we know a little bit about it. We have no horizontal or vertical translation here. It's going to be center origin. So it's a circle with a center at the origin. That's interesting. So the centre would be at 0, 0. I've just used the letter capital C for centre. And it's equal to 2c, so that means that it would have a radius which would equal the square root of twice your constant. So once again, we don't have enough information to confirm what specific circle this is. This is a general solution. So the general solution that we have here is any circle with centre at the origin. Okay, it's an infinite set of solutions. To get a particular solution, we will need some more information. And to follow up, in part B, we are going to now identify a particular solution, and we're given a boundary condition which is the coordinates -2 root 5, which is a point on the curve. So this will hopefully pin down our general solution to a particular solution. Now we have a bit more information. I've just added the coordinates that were given in the question. So we know that -2 root 5 is a point on the curve. Okay, we've talked about it being a circle, and our aim is to find the particular solution to this differential equation. We have the general solution, of course. This is the general solution, x squared plus y squared equals r squared, and we saw that when we added the constant of integration, of course, this would, once with a bit of manipulation, you would get 2c on the right hand side. So I've just made it look more like a circle. Okay, it doesn't really matter, but just to make it clear that r squared would be the 2c. Now then, how do we find the particular solution? So we have an infinite set of circles. Let's just nail it down to one specific circle. Right. Well, it's pretty easy from now on. We just sub everything in as we did previously. So this is your x coordinate here, and this is your y coordinate here. So if we sub those in, we should be able to find a value of r, which would give us a specific radius. You can use 2c, of course, if you want as well. So let's sub them in. So x squared, well, x squared, so that's going to be -2 all squared. So -2, square that, like so. That's x squared plus y squared, so that's going to be plus root 5 all squared. Just being thorough here, guys. Root 5 all squared equals r squared. Alright, so -2 squared, well, that's 4. And root 5 squared, they're inverse operations, that's plus 5. Equals r squared. So 9 equals r squared. So that means that your r is going to be 3. I'm not using -3, of course, because it's a circle, so it can't have a negative radius. But there we go, we've nailed down a particular circle, so it's a circle centre at the origin with a radius of 3.
You have survived, barely, but you must now do the word examples.
Our first worked example is asking us to find a general solution to the differential equation dy by dx subtract y cos x equals 0. And I would like to stress before we begin this that the general solution does not have to be in the form y equals f of x in this case, although it can be an exam requirement to make y the subject once you have found your general solution. And what I will do as we work through these worked examples is to show you how to do that. Some algebraic manipulation is required, and obviously knowledge of exponentials and logs, but I will take you through this step by step. In our first worked example, we are just going to follow the 3 steps that I outlined earlier. Now, I won't write them out, but I will just number them as 1, 2 and 3 at the appropriate point, and then you can refer back to this in your notes. Remember, all the notes you can download. So dy by dx subtract y cos x equals 0. So remember, the first step, which you have hopefully in front of you, is we have to make dy by dx a subject first. Let's do that. So this is step 1. So let's note down what step 1 is over here. So number 1. And without writing it out, I'm just going to do it. So dy by dx is the subject. Well, I need to add y cos x to both sides of this equation. So this will leave me with dy by dx is going to equal y cos x, like so. So we've made dy by dx a subject in 1 step. Next we have to begin the separation of variables process. And as I've stated, because I have dy by dx, I'd like to keep the dy on the left hand side. Just choose a side where you want everything to go. You don't have to do it like this, but because general solutions read y equals f of x in some instances, I'm just going to stick with that format. So dy by dx, so let's call this the y side, and this is going to be the x side. Okay, that's not a step, it's just a note just to remind me what I'm doing. So let's keep dy where it is, and to remove the dx, we're going to have to multiply by it. Remove is in inverted commas, of course. So dy is going to equal y cos x, and then with the multiplication by dx, that's going to go on the end, for obvious reasons in a moment. My red's going, there we go. Okay, let's just have a quick check. So I've got dy there. On the right hand side, I've got a y which shouldn't be there, it needs to be on the left hand side, and because it's multiplying across, I'm going to have to divide by y. So let's divide both sides by y, and this is going to leave me with dy over y. Just doing it in red just to show that this is the active part of the step, if you like. And that's going to equal cos x dx. Great. Let's do another check. So we have y's on the left and x is on the right. Step 2 is finished. So this was step 2. So this was the separating variables, like that. Put all the y's on the left, all the x's on the right. Now we're ready to integrate. So let's just move up to the top of here. So this is going to be step 3, the integration part. So this will get us our general solution. And notice here we have dy over y. If that puts you off what we're going to do next, it may do. I'm going to just rewrite this, and you'll see why. If you're not spotted it already, you'll see why. So I'd like to have something multiplying the dy. That means I can see clearly what the integrand is going to be. And having dy over y, it can make it a little bit more confusing. So what I'm going to do is I'm going to write it as 1 over y, like that, and then dy next to it, which is exactly the same as this. Alright, and I hope you can see the utility of doing that. And that's going to equal cos x dx. Alright, now then, we are ready to integrate. So rather than writing it out again, this time I'm going to put the integration symbol straight in because we have the dy and we have the dx. So let's integrate both sides. Whatever you do to one side, you do to the other in an equation. Now we call upon our integration strategies. You can see how this topic just brings together so many different skills. If I integrate 1 over y with respect to y, you may be more familiar with 1 over x with respect to x. That is the standard integration result, and if you remember, this is going to be the natural log of the modulus of y. Please look it up if you don't know it, and try and learn them. It's good exercise to learn them is write them on cue cards and keep practicing them. So ln of the modulus of y, and we won't write the plus c on the left, we'll save that till the end. That's integrated, standard result. On the right hand side, I'm integrating cos x with respect to x. Again, another standard integration result that we've seen in this chapter. So if we integrate cos x, that is sine x. So this is going to be equal to sine x plus c. We're not asked to give the solution in any particular form. That will essentially do. There's nothing more to say about this. And if we wanted to find a particular solution, we would have to obviously substitute in a value for y and x that coincide with each other, so a pair of coordinates. But as far as general solutions go, that will do it. However, if you're asked to find a general solution in the form y equals f of x, like this, so y equals f of x, that means that we are forced, in order to get full credit on this question, we are forced to make y the subject. Now, how could we do that in this instance? Well, let's have a think. So I've got the natural log of y. To get y as a subject, I'm going to have to use the exponential function on both sides. Okay, we can do that. So if I exponentiate both sides of this equation, we're going to have e to the power the natural log of y is equal to e, and the power is going to be sine x plus c, and the plus c is very important to make sure you get that in, because otherwise your solution will not be the most general solution, and you'll see what I mean in a second. So e to the sine x plus c as the entire power there. We know these are inverse functions, they cancel, so we're going to have y is equal to, now then, e to the sine x plus c. If you know your laws of indices, of course, this is exactly the same as saying, well, it's e to the sine x. So we have a base and then we have an addition in the power. So I can actually write that as a product. So multiplied by e to the power c, okay, using the additive power rule in reverse there. And if you want to, e to the power c is also a constant, because if you have a constant in your power, the constant is just a constant. If you raise that constant, if you use the constant as an index, e to the power of a constant is also a constant. So you might just like to finish this off by saying, okay, well, y equals k e to the sine x, such that k is a constant. Okay, and that would be your general solution. Before we move on to the next example, it might just be worth noting that we can actually check our answers, and if you have time in the exam, you may want to do this because you may be more comfortable with the differentiation process, as tends to be the case. It's not always the case, but a lot of students prefer to differentiate rather than integrate. And we had our general solution given like this, and remember that the differential equation that you were asked to solve, we just make a note of it, was dy by dx. I'll just make a note of it here. So dy by dx, subtract y cos x equals 0. And I want to do this because I want you to see that this does genuinely work. Now then, if we take the general solution and differentiate it, we should be able to set up this differential equation here using our solution. So let's look carefully. We have a rather complex looking function. Now this is a constant, so that's just going to remain at the front, but I have a chain rule situation here. Now I'm going to do this rather quickly, just to get to the point, because this is not about the chain rule, this is about differential equations. So if you'll note, if I want to make a substitution, I could say, all right, y equals k e to the power u, and u is equal to sine x, like that, and I differentiate both of these. So dy by du is just going to be k e to the u, no difference, and du by dx is just going to equal cos x. So the cos x appears straight away. Now remember, dy by dx is going to be the combination of those two, as in the product. So I'm going to multiply these two together to get dy by dx. Before I do that, please note that when I differentiated this here, I got exactly the same result back. So I can just write that as y. So this is just equal to y. Those are equal signs there. That means that when I combine the two derivatives, dy by dx is just going to be the product of y and cos x. And then the next step is trivial, isn't it? So if I subtract y cos x from both sides, I get the differential equation I started with. And in example 2, we are going to again find a general solution to a much more complex differential equation involving trig functions. And again, I will show you how to make y the subject once we have identified a general solution. In example 2, things are starting to heat up a bit. We have a rather nasty looking differential equation here, but we have a 3-step process that will get us to a nice general solution, hopefully. Let's stick with that process, even though you might notice that one of these steps will be perhaps slightly redundant, but this is a particular case only, and if you stick to the steps, you won't go far wrong. So the first step is, of course, to make dy by dx the subject. So let's just write down step 1. And let's see what we can do here. Well, I've got a rather long looking product of 3 terms here. This needs to be subtracted from both sides and then dividing by 2y. So let's do that. So we're going to have 2y dy by dx, and then I'm going to subtract all of this. Is going to equal negative 1 plus y squared cosec x cot x. It doesn't look much better, but let's stick with it. And we said, of course, we can divide now by 2y. So therefore, dy by dx is going to equal negative 1 plus y squared cosec x cot x all over 2y. Now this is the redundant step because there was actually no need to divide by 2y. You may have seen this already if you've looked ahead or you've had a go at it yourself. Dividing by 2y does nothing because we are going to have to make y the y variable on the left and the x variable on the right. I don't have to do that, but if I keep the dy where it is, to get all the y variable terms on the left, I'm going to have to put this 2y back. So that step was redundant, but this won't always be the case, of course. So stick to the process, especially when you're learning this, and then you'll just find it a little bit easier, I think. So let's put the 2y back and embark on step 2, which is to separate the variables. So step 2. So we'll put the 2y back, so I'll do that in red. So we're going to have 2y I hope you can see that. I've got another red pen here, let's try this. Bit better maybe. 2y dy by dx. Okay, and what do I want to do next? Well, I've moved the 2y across. Now I also want to remove the 1 plus y squared from the left hand side, sorry, from the right hand side. So I'm going to divide by 1 plus y squared also. I'm going to leave the negative where it is, and you'll see why in a moment. So I'm going to divide by 1 plus y squared also. There we go. And that's going to leave me with negative cosec x cot x. There we have it. Now I've got the dx there, let's just move that across as well. So we're going to have 2y over 1 plus y squared dy is going to equal negative cosec x cot x dx. You can do the algebraic manipulation in whichever order you like, it's completely up to you, as long as you get everything in the right place. So let's just check this. We have y variables only on the left, and we have x variables only on the right. So next up we're allowed to start doing step 3, which is the integration. So now we've done steps 1 and 2 and we've separated our variables, we are now allowed to start integrating. Let's just have a look at what we've got here. Now let's focus on the left hand side first. We're going to have to integrate a fraction. So let's put the integration symbols at the front. So we're going to integrate 2y over 1 plus y squared. And then on the right hand side, we're going to be integrating negative cosec x cot x with respect to x. That's our task. So let's have a look at the left hand side first and see what we can do. Well, this is a fraction. So we've already outlined in earlier lessons that there are some questions you should ask yourself when integrating fractions. The first question, if I need to remind you, is the numerator the derivative of the denominator? Because if it is, we have a very, very quick solution we can write down. Now if we differentiate 1 plus y squared, we do get the 2y. So this satisfies that question, it answers the question perfectly, and I can write down the answer. Now if you remember, we have a derivative over a function that returns the log of the modulus of the function itself. So I can write the left hand side as follows. So we're going to have the natural log of the modulus of 1 plus y squared. Now that's rather nice, isn't it? So that's really saved us a lot of hardship. Okay, no need to do a lot of work there, no need to use a substitution, just look out for that first of all, and it could save you a lot of time. On the right hand side, this looks horrendous. Now this would be a good opportunity when you see trig products like this, and we have the reciprocal trig functions as well. It's a good time to turn to your formula book, and if you do that, you will notice that this, including the negative, is a standard result. So there's no need to worry. The standard result, when we integrate this, is just cosec x, believe it or not. So again, we have no work to do. We can literally just write down the answer. So the right hand side, and just look it up if you don't believe me, it's just going to be cosec x and then plus c. Once again, we're not asked to give the general solution in any particular form. Were you to do that, we would have to use the exponential function. We would exponentiate both sides, and if you'd like me to do it, I'll do it. So let's just, this is an aside, of course. There's nothing wrong with the answer we've got here, but just in case you want to write it as a function of y. So if we want to write y equals f of x, then we remove the log function by exponentiating. So we would have e to the power of the natural log of 1 plus y squared, and that's going to equal e to the power cosec x plus c. Right, and we've come across this plus c in the power already, so I'm not going to go too much into that. I'll put that in the next step. Inverse functions, we're going to have 1 plus y squared here, which is equal to excuse me, k e to the cosec x. Alright, and then subtract 1 and take the square root, of course. So y is going to equal k e to the cosec x. Forgot to subtract 1 there. Let's do that. Subtract 1, all to the power 1/2. Okay, and that would be the general solution. It's general, of course, because we have the constant in there. Okay, this part is not necessary. There's nothing wrong with this answer here. This is just in case you want to do a little bit more manipulation. And in example 3, as the complexity continues to develop, we are now asked to find a particular solution to the given differential equation. Right, let's consider an approach for this question here. So we have sine squared x dy by dx equals cos x cos y all squared. Something you might want to consider first of all is we have a bracket here which is squared, so let's square the product of cos x and cos y. And if we do that, of course, we'll leave the sine squared x for now. So we'll have sine squared x dy by dx, like so, and square all that, so it's cos squared x cos squared y. Now then, our aim of course is to get dy by dx as the subject. That's the first step. Let's just indicate step 1 here. We just had to square that bracket first. So step 1. Okay, so dy by dx. Let's get it on its own. So we're going to have dy by dx again. Sometimes this is a redundant step. I mean, you can use your common sense. It's just to get you used to the idea. Dy by dx equals cos squared x cos squared y all over sine squared x. I've divided both sides by sine squared x here. Right. Now then, let's just see what needs to be adjusted here. We've got dx here, that needs to be moved over to the right hand side by multiplying by dx. The only term that contains y is here. It's this one. I'll just draw a line over the top of it. It's the cos squared y. That needs to be on the other side. So remember, we're going to keep the y stuff on the left and the x stuff on the right. So with a bit of manipulation, let's work on the y stuff first. I need to remove this cos squared y from the right hand side. So if I divide by cos squared y, that will do it. So this will give me 1 over cos squared y dy by dx will equal cos squared x over sine squared x. And in that one move, I've effectively done everything I need to do, because I have all the y terms on the left and all the x terms on the right. All I need to do now is ensure that the dx is also on the right hand side. So just to finish that little bit off, so this is going to become 1 over cos squared y dy, which is equal to cos squared x over sine squared x dx. Let's put the dx on here. Okay, so we're almost ready to integrate, but we've done the first step. We've made dy by dx a subject, and we've also done the second step where we have rearranged and we are now ready to integrate. So this is step 2. I'll just indicate that over here, which is the separation of variables. So next step is step 3, where we can integrate. Right, I've just rewritten out that step, and we're now moving on to step 3, where we can produce the integration. So I'll just put the integration symbol on both sides here. So we're going to integrate 1 over cos squared with respect to 1 over cos squared y with respect to y. Sorry about that. And cos squared x over sine squared x with respect to x. Before we do that, I mean, you might want to sort of jump in and maybe use substitutions, particularly on the right hand side. Left hand side looks tricky, but if you notice 1 over cos squared, that's a reciprocal trig function. This is the same as sec squared. So let's just convert that into sec squared y. So therefore we're going to have the integral of sec squared y dy. That's an identity, of course, so I'm perfectly entitled to do that. And also we have another identity we can use on the right hand side. We have cos squared over sine squared, which is of course cot squared x. So that's going to equal the integral of cot squared x dx, like that. Right, again, we're going to get the formula book out here. Sec squared, that is a nice integral, a standard integral, and for those of you in the know, this is going to give us tan y. Okay, no complication there. It's a standard result that we can just regurgitate. So the left hand side, let's write that down. So therefore, tan y, and remember we don't need to add the plus c. We're going to do that later. And that's going to equal, now cot squared, you may notice, doesn't actually have a direct antiderivative we can write down. We're going to need to do a little bit more manipulation here. And if you look at your list of standard results, which I don't have in front of me, we don't have cot squared, but we do have cosec squared. We have a standard integral for that, an antiderivative. So if I can replace this with cosec squared somehow, it should make it much more simple. and we have an identity. So let's just write down the identity. So if you remember, cosec squared x is identical to, and I'm running out of room, I'll put it underneath, 1 plus cot squared x. Okay, so that means the cot squared x here I can replace with cosec squared x subtract 1. So let's do that. So it's going to be the integral, and I'll do it in red just so you can see that I've made a substitution here. So this is cosec squared x subtract 1. If I've done that too fast, I apologise. I've just subtracted 1 from both sides of the identity. That's all I've done. You can check that yourself. Okay, let's put that in a bracket. And this is being integrated with respect to x. So now here we have a standard integral we can use. So cosec squared x, we just looked that up. Right, let's write down the next step. So tan y, so therefore tan y is going to equal, now the integral of cosec squared is negative cot x. So that's negative cot x. And the integral of negative 1 is, of course, negative x. Okay, and we can now add our constant of integration. And this has given us the general solution here. This is a general solution. It's a family of curves. But we are given a piece of information. We're given an x value and a y value. So we need to identify what this c is and reduce it down to one particular solution. So let's just make a note of that. So we know that x equals pi over 4 at the same time when y equals pi over 3. We're going to use those two values. If we substitute those two values in, tan of, that's pi over 3, of course, subbing it in, that's y, that's equal to negative cot of x, which is pi over 4. And then we also have to subtract x before we can add c. So that's subtract pi over 4 again and add the constant of integration. We'll now rearrange this to make c the subject and evaluate these trig functions. So tan of pi over 3, you can do that on your calculators. It is a standard result. That's going to give you root 3. Just write that in. So root 3 is going to equal, now the cotangent of pi over 4, that's the reciprocal of tan of pi over 4, which is a nice one. That's just 1, so obviously the reciprocal of that is 1 also, and then minus sign makes it negative. So this is negative 1, and then subtract pi over 4, and then add c. So this means that my constant, I'll just put an implies here, c is going to equal the square root of 3 plus 1 and then plus pi over 4. We are now in a position to write out the particular solution. We're not asked to give it in a particular form where y is the subject, which is nice in this case. So we'll just write out the full solution. So the particular solution my shorthand again, is going to be tan y is equal to negative cot x subtract x, just make that a bit more negative, and then plus root 3 plus 1 plus pi over 4. And it's a nice exercise if you want to. Nice bit of implicit differentiation here. If you want to try and set up the differential equation from scratch using this. Okay, but that is the particular solution. In our last example, example 4, we are again going to find a particular solution to this differential equation, and this will bring together a whole host of different skills that you've accumulated over the past 2 years. The good news in this example is that dy by dx is already the subject of this differential equation. We can skip straight to step 2, which is the separation of variables. So let's have a quick look what we've got. We've got 3x plus 1 and x subtract 1 in the denominator here. They can stay because we're going to put the dx on the right hand side up here. We're going to keep the negative 4. There's no need for that to move. It's unnecessary. But the y minus 3, we are going to need to use some algebraic manipulation to get that on the left hand side. So we can do this in one step. So I'm essentially going to divide both sides of the differential equation by y minus 3 and obviously multiply by dx, and that will get everything in the form we like. So step 2, skipping step 1 of course. Step 2. So we're going to have 1 over y minus 3. dy is equal to negative 4 over 3x plus 1, x subtract 1, dx. Right, just to recap what we've done here, so we divided both sides by y minus 3 and kept the negative 4 there, and we've multiplied both sides by dx. Everything is in the form we need. We are now ready to integrate essentially, but it's not quite as simple as that, as you'll see. If you look at the left hand side, we have 1 over y subtract 3. So again, go through your questions. Is the numerator the derivative of the denominator? Yes. With respect to y, of course. So this is straightforward. We can just write this as a logarithm of y minus 3. That's fine, that's done. The problem arises with the right hand side. Now, if we expanded this out, this would give us a quadratic, and quadratics obviously have an order of 2, or power of 2 in other words. The differentiation process will reduce that power by 1, which would mean that you would have a constant x term, beg your pardon, an x power of 1 in the numerator, a linear power. Now that means that the negative 4 is in no way going to be the derivative of the denominator. So we can't use that first rule. The only option here is to use partial fractions, which is what we're going to do now. So we're going to work on the left, no we're not, we're going to work on the right hand side. So right hand side. And I'll just make a note what we're going to do. We're going to use partial fractions. Use partial fractions. These are for your notes, of course, just to remind you when you're going over this and you're revising, you know what the thought process is. Right, so let's set up the partial fractions. We have 2 linear factors in the denominator. That means we're going to have 2 separate linear terms in the denominator for our partial fractions. So we're going to have negative 4 over 3 lots of x plus 1 and x subtract 1 must be identical to some constant over 3x plus 1 plus some other constant b, which we'll call it, over x subtract 1. And that's basically what I was trying to say in my ramble a few minutes ago. Right, so again, on the right hand side, in this particular identity, we're going to have to reconstruct this fraction here and equate coefficients. So that means, and you've done this lots of times now, so -4 must be identical to a multiplying x subtract 1 plus b multiplying 3x plus 1. I'm not doing all the steps here because we've done this many times now. Okay, you can put in as many steps as you like, but I think that will do it. We can disregard the denominators because they of course will both be the product of these two. Right, so we're going to equate them. It's up to you how you want to do it. I'm just going to expand and set up the equations. You can use substitution if you like. So -4 is going to be identical to ax subtract a plus 3bx plus b. And we'll set up the equations up here on the right hand side. So first up, let's look at the x's. I'll just partition my working. So x's, well, what do we have? Well, we've got a lots of x here, 3b lots of x here on the right, and no x on the left. So we know a plus 3b must equal 0. There we go, okay. And we also have constants to look at. So constants, just write that as C's. It doesn't matter, it's just for your reference as long as you know what you mean. Constants, well, we've got -4 here, but on the right hand side we have -a there, plus b must equal -4. Let's write that down. So -a plus a single b must equal -4. We now have two equations. So we'll call this equation 1 and equation 2. And we solve simultaneously. I hope it's pretty clear. We just add them together, the a's will cancel. So let's do that. So this will give us, so 1 plus 2, equation 1 plus equation 2, of course. 4b will equal -4, just adding all that together, which means b must be -1. So therefore b equals -1. Straightforward, nice constant there, no fractions. And then to get a, we sub b equals -1 into, let's say, 2. So sub b equals -1 in equation 2. Pick whichever equation you want, doesn't matter, it should work. So -a, therefore -a plus, now b is negative, so that's -1, equals -4, -4. So -a, subtract 1 equals -4, add 1 to both sides, so -a is equal to -3, so therefore a equals 3. Great, so we've got the constants. That means our partial fractions are done and we are ready to proceed to step 3. Right, so I've rewritten out what we had previously and we're about to embark on step 3. I've made an adjustment, of course, because we now have the partial fractions, well, we calculated a and b in the previous step. I've made a direct substitution of the -4 over the product of 3x plus 1 and x subtract 1. I've replaced that with our partial fractions. So now, yes, we can go ahead and integrate, and I've just left the boundary conditions here that we were given. Okay, let's integrate both sides. So integration sign and integration sign here, just squeeze that in and everything is ready to go. So on the On the left hand side, I'm going to do that directly. We've talked about that. The numerator is the derivative of the denominator. So we're going to have the natural log of the modulus of y subtract 3. No need to add the constant yet. On the right hand side, we're integrating 3 over 3x plus 1. So let's ask ourselves the question. And the answer to the first question is, of course, yes. The numerator is the derivative of the denominator. That is very fortunate indeed. So this is going to equal the natural log of 3x add 1. This is going well, and then we do it term by term. We're going to integrate 1 over x subtract 1. It's negative, so I'll leave the negative here, and we'll just focus on the 1 over x subtract 1. And again, the numerator is the derivative of the denominator. So I can write this as ln of x subtract 1 in the modulus. Right, because we have logarithms everywhere, when we add the constant of integration, it's good practice to write the constant as a logarithm. Well, I've been over this in some detail in a previous lesson. So I'm going to add the constant and I'm going to write it in this form. So it's going to be plus ln of k, and we'll just make a note that k is a constant. And just as an extra restriction here, remember k cannot be negative, so k must be greater than 0. It doesn't matter, of course, in the logarithm, because if you take the log of any positive number, you can return any value on the real number line. So this is any real number, that's no problem at all, but the k specifically has to be positive. All right, this is looking good. Now, this is the general solution, essentially. We're not asked to write it in a particular form at all. So why don't we just go ahead and substitute in our boundary conditions and let's see what we get. Okay, that will nail down a particular solution. Okay, so y is 17. So we're going to sub in 17. So for the particular solution, we're going to have, yes, so log of 17 subtract 3. So 17, I hope you can see that, is equal to the natural log, and then it's going to be 3 lots of 2. So 3 times 2. Like so, plus 1, and then subtract the natural log of 2 again, subtract 1. Apologies for the green here, it's not looking good, is it? And then plus the log k on the end. Alright, so some evaluating to do here. So that's going to be ln of 14 is equal to 3 lots of 2 is 6 plus 1 ln 7. Nice link up there. Subtract ln of 1 plus ln of k. Right, let's see what we've got. Well, natural log of 1, as we should all know now, you're all saying it, I hope, 0. Okay, let's just rearrange. So we have ln 14, ln 7. Right, so let's bring the ln 7 over to the left by subtracting it from both sides. So ln of 14 subtract ln of 7 will equal ln of k. I can now use the division law. So we have same base, natural base e, of course, natural log. So 14 divided by 7, that's obviously 2. So ln of 2 equals ln of k, and I can just remove the logarithms now. So that means k equals 2, or 2 equals k in this case. Alright, so we have our k. That means that we can now I've just thrown a bit of my pen on the floor, never mind. We can now write down our particular solution and we can get it in a nice looking form. In the final steps now, I've just written out our particular solution. We've got k was 2. There's nothing wrong with this, and the question doesn't ask you to write it in a particular form, but I'm going to stress that it's good practice to be able to manipulate log equations like this and write them in the form y equals f of x. It may be asked of you, and in this particular situation we do get a nice function at the end. So I'm going to write this as a challenge, and I'd like you to put this in your notes also. So challenge, so find out what y is as the subject. It's going to be a function of x, so hence find out what the function of x is. How do we do that? Well, there's logs everywhere, and we're going to see why writing this as a log was so useful. We've got x stuff on the right and y stuff on the left, if you pardon my parlance. Can we use any particular laws? Well, yes, we've got base e everywhere. Let's use some of the addition laws and the subtraction laws for logarithms. So let's keep the ln of y subtract 3 where it is for the time being. Now here, in the first two terms, we have a subtraction. So that means I can write 3x add 1 over x subtract 1 all as a single modulus. That's good, so let's do that. So that's going to be the natural log of 3x plus 1 over x subtract 1 plus natural log of 2. Okay, good stuff. We now have same base e, and we have an addition. That means I can combine these two using the addition law, multiplication law, however you want to call it. So this is going to be ln of y subtract 3 is going to equal the natural log of 2 lots of, now, 3x plus 1 over x subtract 1, combining those two logarithms as a product. So it's the log of all of this, and remember 2 is positive, so there's no need to mod it. Right, we can now just dispense with the logs. We have the log of all of this is equal to the log of all this. The logs are not necessary anymore. So we now have y subtract 3 is equal to 2 lots of 3x add 1 over x subtract 1. Like that. Okay. You might be wondering as well, why do we not keep the modulus? Well, the modulus is a restriction based on the log function. It's the log function that forces us to make the restriction. Once you remove the log functions from both sides, that restriction no longer applies. Okay, so let's add 3 to both sides. So we now have y is equal to 3 plus, now I'm going to just multiply this out, so that's going to be 6x plus 2 over x subtract 1. And that's essentially the answer, but can we do even better? Can we combine this into a single fraction? I think we should have a go at that. So I'm going to move my working out up here, like so. So let's write everything over x subtract 1. So we're going to have y equals 3 lots of x subtract 1 add 6x plus 2. Just fit that on, hopefully. Yeah. All over x subtract 1. Alright, so therefore it's coming together now. We have 3x subtract 3 add 6x add 2 all over x subtract 1, and finally let's collect like terms. 6x plus 3x, that's 9x. Minus 3 add 1 is -1 all over x subtract 1. And that's a nice function. You could sketch that quite nicely. Okay, there's our particular solution, looking really good there.